All right. Good morning again, everyone. How is your day? I hope it's going well. Aside from, I understand that you really have a lot on your plate insofar as Cal 2 is concerned, because I heard you just finished section 8.4, which is integration by partial fraction decomposition. And then you're still, I think, you're still trying to get hold of doing long solutions in trigonometric substitution and so on. But another thing is that I just found out that the deadline for regrading requests of the pre-response part of test number 2 is tonight at midnight. So I hope you guys have already seen the pre-response part of your test. If you haven't done so, kindly take a look at it this afternoon. And then if you feel that there's some grading errors that were done, or you think you should have gotten some more points out of some of the problems, then let me know. Send me the PDF file of your graded free response part together with the original file name that you got when you downloaded it from CASA. Send it to me via email or via chat here in Teams. And then together with a question on the body of your email or your chat, let me know what is your specific question. Then I'll take a look at it, evaluate your case, and then make some proper recommendations for the correction. So I receive two regrading requests from yesterday, and I already responded to both of them. So if you still have some questions, then let me know. Okay, and then for our poll, two other people answered, but they are still evenly split. So probably what I'll do is just to answer one more question about trigonometric substitution, and then go quickly into partial fraction decomposition. All right, I guess that's fair. Okay, just as a quick recap, we did trigonometric substitution last time, and we said that the principle then is that trigonometric substitution might be able to free us up from radicals in the integrand, right? So if your integrand has radicals of one of these three forms, then you can use some of the Pythagorean identities in order to eliminate the radical. So for instance, if you have a squared minus x squared inside the radical, then letting x be equal to a sine theta will let us to take advantage of the identity 1 minus sine squared theta equals cosine squared theta. And since you have a cosine squared theta after some manipulations, then the square root will be gone. And the same thing for a squared plus x squared. The only difference is that the motivating identity here is that 1 plus tangent squared theta equals secant squared theta. So we want to replace x squared by a squared tangent squared theta, so that we can use the identity secant squared theta. All right. And the same thing for secant. And I guess last time we considered 3 examples, I guess. But you might have realized that trigonometric substitution results to very long solutions because it will take a while before you can simplify the original integral. And then in the integral, you might be dealt with integrals that require techniques from section 8.3 or will require some trigonometric identities. So that's another difficulty with this method. So use this as your last resort. I mean, try some integration formulas first, or try U substitution. And when all of those fail, then that's the only time that you should try trigonometric substitution. Let me just see what are the problems we looked at last time. So we had a basic one, which spanned 3 pages, and then we also considered one wherein we need to do a U substitution first before realizing what would be the proper trigonometric substitution. All right, so let's write this one. This is an additional problem. So this is not from the problems in the worksheet. At least I don't think it is. So let's write this one. Let's say we want to evaluate the integral of x cubed times the root of 4 minus 9x squared dx. Okay, here, I guess there is a way wherein we can make u substitution work here, but just for the sake of illustrating trig sub, I'll do trig substitution here, which might be which is ironic since I told you to use trig sub as a last resort. But anyway, so I just want to drive at the point wherein both terms inside the radical has some constants in there, and how to choose the proper trigonometric substitution. So here, just oops. Okay, so I'll leave with those highlighted ones. But anyway, so here you see that the radical is 4 minus 9x squared. It screams the use of sine theta, right? So it looks like a squared minus x squared. But the thing is, you have a constant in front of x squared. So, but essentially what you want to happen is that you want 9x squared to be replaced by 4 sine squared theta, right? That's our hope, to be able to replace 9x squared by 4 sine squared theta. Because if that will happen, then the radical will be 4 minus 4 sine squared theta. You can factor out the 4 and be left with 1 minus sine squared theta. And use Pythagorean identity will tell us this is 4 cosine squared theta, right? That's what we want to happen. So for that to happen, I want 4 sine squared theta to replace entirely 9x squared. So that's our hope. 9x squared will be replaced entirely by 4 sine squared theta. So this is our goal. Find the right substitution so that this will occur. But this will occur if we take the square root of both sides and get 2 sine theta equals 3x. So I just took the square root of both sides and then divide both sides by 3 will tell us that x should be taken to be 2/3 sine of theta. And that would be our trig sub for this problem. And if that's the case, then dx will be 2/3 cosine theta d theta. And I guess now we're ready to put this into play into the original integral. So we have x cubed. So that would be 2/3 sine theta to the third. Okay, that's x cubed times the square root of 4 minus 9 times 2/3 sine theta quantity squared times dx, which is 2/3 cosine theta d theta. Okay, so that's what will happen when we do the substitution. But essentially, this is what? Okay, I see that I have a 2/3 to the third power there. I have another 2/3 in the du part. So I can put them out of the integral and write them as 2/3 to the fourth power times the integral of sine cube theta. And then remember what will happen here? 4 minus 9x squared essentially will be 4 minus 4 sine squared theta, because that's what we wanted. Or actually, I wrote that here, that 9x squared will be replaced by 4 sine squared theta times cosine theta d theta. Okay. And then we know what will happen here. We'll have 2 to the 4th over 3 to the 4th of sine cubed theta. And then here we'll have 4 times 1 minus sine squared theta cosine theta d theta. We already knew that this will happen. I just included them for the sake of solution so that when you review these notes, you know what exactly occurred. But if you already knew that will happen, then I guess you can skip this in your solutions because that's a straightforward identity. But this would be 2 to the fourth, 3 to the fourth, sine cube theta. And this would be 2 square root of cosine theta, or cosine squared theta, cosine theta, d theta, which is again a non-necessary part of the solution. You can skip this. But again, I'm just putting all details so that you can review these notes completely. So you have sine cube theta, cosine theta out of the square root, another cosine theta outside, and we're left with this. Or ultimately, this is what we need to integrate. All good? So I hope you were with me during that calculations. Okay, now what do you think should be done at this particular integral? How do we evaluate this? I hope that form is familiar with you. Anybody? Do you remember what to do with this integral?
Let's split the sign into even.
That's correct. Because if you remember, this is one of the cases from powers of trig functions. So he's right. We can isolate a power of, or a single sign, right? Because you have an odd power for sign. And whenever you have such, you can take one of those signs and reserve that for the du, right? That will be reserved for the du. And if that is our intent, or if we intend to use that for our du, then should be cosine theta, right? So the beauty of taking a sign out of an odd power is that that will leave us with an even power of sine, which can easily be expressed in terms of cosine using the Pythagorean identity. So essentially here, the next thing is, have 2 to the fifth over 3 to the fourth, 1 minus cosine squared theta, cosine squared theta, sine theta, d theta. Then here we let u be equal to cosine theta. Du is negative sine theta d theta, as we planned. So you have a negative sign for the du. I can put that out here. 2 to the fifth, 3 to the fourth, times 1 minus u squared times u squared times du. Okay? And so this is negative 2 to the fifth over 3 to the fourth. Integral of u squared minus u to the fourth du. Okay? And then now it's easy to integrate because it's just a polynomial in the variable u. So this would be u to the third all over 3 minus u to the fifth all over 5 plus the arbitrary constant c. Okay? And then we revert to the original to the variable theta. Remember, we let u be equal to cosine theta. So let me just go back to theta. So this is cosine cube theta all over 3 minus cosine to the fifth theta all over 5 plus arbitrary constant c. But remember, we are originally dealt with an integral in the variable x. So we need to go back to x. So, but remember, we let x be equal to 2/3 sine theta from above, right? So that means sine theta is equal to 3x over 2. And from SOHCAHTOA, sine is opposite over hypotenuse. So what we do, draw a right triangle. Say the right angle is over there. Let theta be here. And then opposite theta should be 3x units, right? Because that's opposite. And then the hypotenuse is 2. And then the third leg can be computed using a Pythagorean identity. That's going to be 4 minus 9x squared. And I knew that my this substitution makes sense because I ended up with the original radical, right? Let me just put that on the side here. So if that's the case, then what do we see? So that means cosine theta is equal to, cosine is adjacent over hypotenuse. So adjacent to theta is this, root of 4 minus 9x squared over hypotenuse, which is 2. Okay, so we'll use this here. So we'll have negative 2 to the 5th over 3 to the 4th times cosine theta cubed. So that's, I'll put the 1/3 first. And then cosine theta is root of 4 minus 9x squared all over 2 to the 3rd power minus 1/5 root of 4 minus 9x squared over 2 to the 5th plus the arbitrary constant c. All right. Okay, you're good, Fatuma. Anyway, going back here, any other question? Is there any problem with this? Aside from the length of the solution? Well, Kevin, just bring some patience with you. The key thing here is that you know what's the proper U substitution. Because I understand the process is long and it might be daunting, especially this is your first time seeing the method. Actually, this is the method that I hate the most because it's quite long. Make sure you know how to pick the right U substitution, because I guess that's the most crucial part. Or sorry, the right trig substitution. That's the most crucial part. And then slowly but surely try to transform the given integral in terms of the new variable theta. Okay. And that will take some patience to do. You need to do some algebraic manipulation. You need to employ some trigonometric identities. And then once you are able to simplify, you'll get to this point. But that integral there is something that you could have seen, or that you have seen in section 8.3. So basically, this is not a standalone section, because you might need some things that you have learned from the previous section to solve problems like this. So I guess I mentioned to you guys last time that if I want to torment you in the next exam, I could write one single problem that will require you to use all of the things or all of the methods of integration that we have encountered in section 8. That's very possible, but it will take you an hour or so to finish it. But don't worry, that won't happen. You will be given separate integrals to work on. I'm hoping that they will not be as long as this one, but who knows, right? Okay. Now, do you have any questions about the trigonometric substitution? Do you want to do one more problem, or should we jump to partial fraction decomposition? Because I learned that you just finished, you just finished section 8.4 today, but yeah. And I think it's just watching somebody do trig sub and doing it on your own are two different things. It might look straightforward when you're just watching it with somebody, or it seems easy but long if you're doing it with somebody. But doing it on your own might be different. So we can go on to partial fraction decomposition, but I hope you guys will take some time to practice with trig sub. All right. Okay, Kevin is suggesting we move on. How about the others? Do you agree? Okay, nobody wants to decide. So if that's the case, then I'm going to move on. to partial fraction decomposition. Let's see, where's worksheet 11? I uploaded a blank version of worksheet 11, but again, this is just a compilation of the chapter exercises from the textbook. So let's see. The main idea about partial fraction decomposition is on how to integrate a rational function. Oops. Okay, so we want to integrate p of x over q of x dx. Now, after some substitution or after some preliminary steps, you should have a polynomial in x over a polynomial in x, then you integrate it. So p and q are polynomials. First thing to do is to check if the degree of the denominator is strictly larger than the degree of the numerator. If that's the case, then we can move on to step number 2. So if it is not, then you need to do long division. Because partial fraction decomposition only works when the degree of the top is strictly less than the degree of the denominator, right? So make sure you got that right first. And then the next thing is to factor the denominator. Okay, so essentially what we'll have is, okay, say q of x is equal to q1 of x times q2 of x until q sub n of x. So you try to factor it completely. Make sure to factor everything that is factorable. Otherwise, partial fraction decomposition might not work, okay? So Q1 until Q capital N are all irreducible or non-factorable expressions anymore, right? Why do we want them to be irreducible or not factorable anymore? Because the form of all those factors will tell us how to decompose the big fraction into several little fractions, right? So now for the decomposition, so each of the factors will force us to have some little fractions on the decomposition, and how those little fractions look like will depend on how the factors look like. So for instance, we have case number 1. Oops. If there are no repeated factors, meaning Q1, Q2, and Qn only have exponent 1, or there are no repeated factors, then Q1, or one of those factors, will lead into one little fraction, which has itself as denominator, but the numerator would be 1 degree less. So what do I mean? So if Q1 says a linear function, it is not repeated. So it is a factor of multiplicity 1. So Q1 is linear, so it's degree 1. So the numerator will be a generic constant because we expect the numerator to be involved. Okay. Now, if Q1 happens to be quadratic, so it has degree 2, then the numerator will have degree 1. Now, it is a lot more complicated if there are repeated factors. So if there are repeated factors, say Q1 is degree n and repeated m times, then Q1 will force us to have this in the decomposition. Since it is repeated m times, there would be m little fractions that will be induced by Q1. And what would be the denominators for those fractions? They would be increasing powers of Q1. So here you will have Q1, and this is Q1 squared, Q1 cubed, until Q1 to the m, because it should be repeated m times with increasing exponents. But the numerator is degree n minus 1. Okay. So if Q1 is of degree 2, then all the generic numerators will be of degree 1 less than the original. Okay. So the numerators will all have the same degrees. There will be generic polynomials of degree capital N minus 1, but they will have different denominators. Again, that might be a lot to take in. So probably it's better to do some examples and observe how these two cases come into play. So let's try some examples. Sorry. Let's try problem 17 first, because this, I guess, is easy. Okay. So we're lucky here because the denominator is already factored. The numerator is 7, which is degree 0. The denominator is quadratic, it's degree 2. So first step is a check. Degree of the bottom is greater than the degree of the top. And then the next step is to factor. Luckily, the factorization was done for us. And now we need to do the decomposition. So now we have 7 over x minus 2 times x plus 5. We want to decompose it into little fractions, okay? Now let's observe the factors in the denominator. The first is a non-repeated factor. X minus 2 only appeared once as a factor. So it gets one little fraction in the decomposition. X plus 5 is also non-repeated. So it gets one partial fraction, okay? And then the numerators are generic polynomials of 1 degree less than the denominator. The first denominator is linear, degree 1. So the numerator should be a generic degree 0 polynomial. But a degree 0 polynomial is just a constant. So this should be a generic constant. Let's call it A for now. And then also for the second term, we'll have a generic constant. Let's call it B as your numerator. Okay. Now, we want to solve for the values of A and B. So if we want to do that, then I'll perform the multiplication on the left-hand, the addition on the left-hand side, just for us to know what A and B are. So if you do so, you'll have A times x plus 5 plus B times x minus 2 all over x minus 2 times x plus 5. That's the simplified form of the right-hand side. But again, that will still be equal with the left-hand side. So we'll have this, okay? And for this equation to be true, since you see that the denominators are equal, this denominator is equal to that denominator. For this fraction then to be equal to this fraction, then their numerators must also be equal to each other, right? So that means 7 must be equal to A times x plus 5 plus B times x minus 2 for all x's. So that should be true for any value of x, okay? Now, how do we solve for A and B? You can have a system of linear equations by giving in special values for x, but you can take advantage of the fact that this equation that we currently have is true for any x. So you can pick any x, and we can choose any x, right? So here, actually we have some convenient choices for x. Say, I can let x be equal to -5. why do I want to let x to be equal to -5? Because if that happens, then if I plug in -5 into the x's I see in the previous equation, I'm going to have 7 equals a times -5 plus 5, that's going to be 0. And then a will be gone from the picture, right? But for b, we'll have b times -5 minus 2 will get -7. And so we'll have 7 equals -7b. Solve for b, you get -1. All right. Now moving on to the next one. If x is equal to, what would be the nice choice for x? Again, in theory, you could select any value for x. But again, it would be more convenient if I will let x to be equal to 2. Because if x is equal to 2, then I'll have 7 equals 7a plus b times 0. All right. And that means 7 equals 7a, which implies a is equal to 1. And now we have, at least on paper, what's the proper partial fraction decomposition for the original expression, right? So therefore, the original integral, 7 over x minus 2 times x plus 5 dx is equal to, the integrand can be decomposed into 1 over x minus 2 plus -1 over x plus 5 dx. And this is the partial fraction decomposition of the integrand. And the nice thing about the decomposition is that in theory, it should be easier to integrate the pieces, the partial fractions, because they have less complicated denominators, right? And true enough, if you carry on, if you carry on with the integration, these are just a bunch of ln's. In particular, this is ln of absolute value of x minus 2 minus this is ln of x plus 5 plus the arbitrary constant c. All right. Is that clear? Okay, I'll take that as a yes. Any questions? I noticed that as the semester goes on, you're starting to be more quiet and more quiet. Well, nice, good question, Kevin. The solution will be an ln if actually it depends really on the partial fractions. If you have a constant over linear, definitely it will involve an ln. But if you have a constant over a quadratic, that could be an arctan. Can be or if you have x over a square, that can be an ln, that can also be an arctan. So there's no hard and fast rule unless we see exactly how the denominators look like, right? Okay, let's see another example, and hopefully we can illustrate some of the other cases just to answer Kevin's question more fully. Let me see. Okay, should we go on with the more exciting problems now? Let's see. Okay. Let us do problem. Let's do problem 26. More exciting. You don't want to. You don't want the sound of more exciting problems. Yeah, but these are the problems that probably you will meet in the quizzes. So let's maybe we should try many such examples so that you get numb to it. And when you see them in the quizzes, they are not exciting anymore. Okay, let's try problem 26. Now, first check, is the degree of the denominator higher than the degree of the numerator? The denominator is degree 3. The numerator is degree 2. Luckily, no need for long division. Okay. Next, factor the denominator. Now the denominator luckily is also factored. X minus 1 quantity squared cannot be factored anymore. X plus 1 cannot be factored anymore, so it's completely factored. It looks like the problem is very generous to us, but actually I guess it will escalate quickly once we do the partial fraction decomposition. Okay, now partial fraction decomposition, x squared over x minus 1 squared, x plus 1. Okay, now we expect to decompose this one big fraction into little fractions, right? And the form of the little fractions will depend on the factors in the denominator. So the first factor in the denominator is x minus 1 quantity squared. The factor here is x minus 1, but it is repeated twice, right? Because it has an exponent too. That is what we mean by repeated factors. Because if you will rewrite this, you will have x minus 1 times x minus 1 times x plus 1. So x minus 1 is repeated twice, okay? So since it is repeated twice, it will get two little fractions under its name, okay? The first little fraction will have x minus 1. The second will have x minus 1 quantity squared. This is what I tried to explain later with the use of capital M. So if it is repeated m times, then you will have m little fractions with denominators each a power of x minus 1. Okay? And then what was the repeated factor? The repeated factor is actually, x minus 1. It's linear. It's linear, so it's the numerator of the little fractions that came out of x minus 1 should be generic constants, okay? So this must be a generic constant. This must be a generic constant. And we need to solve for a and b, all right? Unfortunately, this is just for x minus 1. We still have another factor, but thankfully, that factor is non-repeated. It's non-repeated, so it only gets one little fraction with itself as denominator. That second factor is linear, so the numerator should be a generic constant. Let me call the generic constant d. Okay, I will use d because, why do I want to use d? I want to use d because I am reserving the arbitrary constant c to be the one to be added after the integration. All right. Okay. Now you have two options here. First, you can compute for the values of a, b, and d as what we did before. But if you look at this decomposition, it looks a little easy to integrate both sides here. I mean, you can do the integration first and then solve for a, b, and d later. That works for some examples. I guess that will work here. So note that here, I can do it this way, just to give a different flavor than what we did before. Actually, I prefer doing it here whenever possible so that you get, because I usually give more partial credits whenever you're doing the calculus stuff rather than algebraic stuff. So it would be good to finish all the calculus steps, then worry about the algebraic solution to a, b, and d later, okay? So now with this partial fraction decomposition, I know that the original integral can be written this way. Okay. It's just that we don't know what the values of a, b, and d are, right? Now, for the first term, it is a over x minus 1. A is a constant, so a can come out right away of the integral. So we are integrating dx over x minus 1 for the first term. For this, I can let u to be equal to x minus 1. Du is dx. So this would be integral of du over u. So that's going to be ln of the absolute value of u plus some arbitrary constant, right? So basically, the first integral will be ln of the absolute value of x minus 1 plus some arbitrary constant. A is a constant we don't know the value of yet, right? That's fine. And similarly, for the third integral, or for the third term in the integral, this would be d ln of the absolute value of x plus 1, right? So to integrate that, you simply let u to be equal to x plus 1. You'll have du over u, which has an ln as its integral. Okay? Now, the problem would be on the middle term, but actually that's not a big problem. So you are integrating b over x minus 1 squared dx. You can take b out of the integral because it is just an this is just an undetermined constant, okay? And then here I can still let u to be equal to x minus 1. Du is equal to dx. So this guy will be b integral of du over u squared, okay? And this would be b u to the negative 1 over negative 1 plus some arbitrary constant c. So the middle integral then is b times x minus 1 to the negative 1 all over negative 1. Is that good? And this, Kevin, is one example wherein we don't get a tangent. We don't get an ln out of the integral. Okay, is this good, guys? Before I delete that solution for the middle integral. Okay. So let's delete this part. Okay, so let me just rewrite the answer here. It's going to be a ln of x minus 1 minus b over x minus 1 plus d ln of x plus 1. Oops, I forgot the plus c. That's a minus 1 deduction if it was an exam. So better put those c's in there. Okay. Now what's left to be determined are the exact values of a, b, and d. Okay. And for that, we'll do the same thing as what we did before. So let me just copy this. And actually here you have done all the calculus step. All that remains is to perform algebraic methods in order to solve a, b, and d, which might take longer than the actual calculus steps. If grading is up to me, then I usually give more points for doing the calculus stuff. So I encourage students to perform the calculus stuff first, because you might not have enough time to go back and do the algebraic manipulations for a, b, and d. And this is a calculus class, so the priority should be for you to be able to carry out all the calculus steps. Okay, let me just plug my iPad in. Okay, there we go. All right, now how to solve for a, b, and d? Well, we'll employ the same process as what we did before. So note that x squared over x minus 1 squared times x plus 1 is equal to just a little fraction over here. So we perform the addition on the right-hand side and get a times x minus 1 plus b, there's an extra x plus 1 here, plus b times x plus 1 plus d times x minus 1 squared. Okay? I hope you remember how to add fractions, algebraic fractions. Okay? Now, again, you can we know that this should be true for all x's. Okay. This is a silver lining of online classes for me. I can do copy pasting without having to write everything over and over again. Okay. And this should be true for all x's. Okay. So we have the liberty to choose what x's, x's that are more convenient for us. Okay. So I guess, for instance, here, usually it's convenient to choose x's that will make the factors equal to 0. Okay, but you will see later that I will run out of good options, so I will resort to choosing some values for x that are small or more convenient for me. Yeah, Kevin, you're correct. We can start by choosing x to be equal to 1. So plug x equals 1 in the entire equation. So the right-hand side will be 1. Or the left-hand side will be 1. And then the first term will be 0. Second term will be 2b. And then the third term will also be 0. So that gives us the first constant. B is equal to 1/2. Okay, what's next? Another good option for x would be -1, right? So if x is -1, then we'll have 1 on the left side, and then the coefficient of a will be 0, the coefficient of b will be 0, the coefficient of d would be -1 minus 1, that's going to be -2 quantity squared. So that means 1 is equal to 4d. So that means d is equal to 1/4. Okay. Now we don't have any other choice for x that will make one of the factors equal to 0. But again, this equation is true for any value of x. So you can pick any x you want. You can pick x equals pi, x equals e, x equals 17, x equals 1,000,000, x equals 10. It's up to you. I don't know why you will choose that, but choose x equals 0. Maybe that would be more easier to manipulate. So the right-hand side, the left side will be 0 equals. So we are plugging in 0. So I'll guess we'll have -a. And then if I plug in 0, I'll get a b. And then if I plug in 0, I'll get a d. Okay, is that correct? So you plug in 0 for all the x's that you see in this equation. Let me highlight the equation here. This is where we are plugging these values of x into. Because again, this is true for any x, so you can pick any x you want. And then we have an equation here with 3 of the constants involved, but luckily we already knew 2 of them, right? So we don't know a, so leave it there. We already know b to be 1/2. We already know d to be 1/4. And so we have this. So 0 equals -a plus 3/4. And so here we see that -3/4 is equal to -a. That means a is equal to 3/4. Good. And now to complete the solution, I'll need to go back to the integral we computed earlier. Okay. Let me just copy this guy. Okay. And I guess this is this PDF annotator is one of the best dollars I spent in gaming apps or in general apps and softwares, because it saves me time just copy pasting things. Okay. All right, so let's now plug in the values that we found. A is 3/4. What is b? B is 1/2. So that's -1/2x minus 1. And then d is 1/4. Plus the arbitrary constant c. Okay, is that good, guys? For me, it's easier than trigonometric sub. So I hope it is also for you guys. But this is it's still a, it's still a primitive case or a simple case because we have a repeated linear function. Yeah, you're right, Kevin. The hard work here would be on splitting it up, and then the integrating would be a little bit easier. Okay. Now, this is still a primitive example because you see that the repeated term is, or the repeated factor is only linear and it's only repeated twice. Okay. The complication will happen if you have repeated nonlinear factors. So probably we'll do it on Friday. We'll look at some examples like, say, like example like example 32. For example 32, you have a quadratic factor here and another quadratic factor here. Both quadratic factors are not factorable anymore. So in the partial fraction decomposition, x squared plus 1 will have a linear numerator, as well as x squared plus 3. So basically, as a sneak peek, this will be the integral of a generic linear function over x squared plus 1 plus another generic linear factor over x squared plus 3. Because even though these quadratic factors are not repeated, this is quadratic. And again, as I mentioned earlier, for non-repeated factors, it will get one little fraction in the decomposition, but the numerator would be 1 degree less than itself. It's degree 2, so the numerator should be degree 1. The same thing here. So even though we only have 2 fractions involved in here, we need to solve for 4 constants, a, b, d, and e. And then integrating these terms is another thing, right? So I guess here we can integrate it by separating it further and so on. So we'll look at it on Friday. Another interesting case is this. You have a repeated repeated quadratic factor. So the decomposition here will look like, okay, I have x squared plus 4. It's repeated twice, so it will get 2 factors in the decomposition. And then the numerators of this little fractions will be 1 degree less than the original factor's degree. So the original factor here is x squared plus 4. So that means it will get an ax plus b on top. And the second one will also have a generic linear function on top. So you get 4 unknowns, a, b, d, and e. And I guess integrating this guy would be another thing. Okay, and it will really depend on d and e. For those cases, we need to solve for a, b, d, and e first before performing the u substitution. Okay, so get ready for more exciting examples on Friday. But I hope by then you will have the time to try problems 30 and 32, because probably I'll start with these 2 on Friday. So if you have questions on these, let's settle them on Friday. Okay? But before I let you go, again, the deadline for regrading requests is tonight at midnight. So make sure to find some time in the afternoon to take a look at your exam and let me know right away before midnight tonight if you feel you should have gotten more points or partial credits for a certain problem. Okay, guys, so that's it for me today. So have a good day, and let's see each other again on Friday. Bye, everyone.